Good afternoon, I'm Adib Mahmoud. This time I'm so sorry for the internet problem. So I will start my presentation once again. So our job for this semester was to implement a local planner based on the Frenet optimal trajectory. Since Bean already explained what Frenet frame is and I explained it last semester, I will skip this part. So this is where we left off last semester. I had a problem with the cubic spline planner, which was used to generate 2D spline from a given dense global waypoints. Debugging showed that a divide by zero error was occurring whenever I entered the entire global trajectory. So the plans I made last semester for this semester was to figure out how to solve this Frenet Cartesian transformation problem. And in most open source code, they only had the velocity keeping behavior. However, my plan was to also add following a leading vehicle maneuver, merging, stopping, and stuff for real world use. And thanks to Dong So, he's a student in the Urban Robotics Lab. He pointed me to an alternative library to the cubic spline planner, which solved my transformation problem. And regarding adding different maneuvers, so this is what was coded already in the open source code. So in here, what the ego vehicle basically does is it generates a trajectory which will allow it to maintain a desired velocity. However, what if there's a car up front? So I've seen some people, what they do is that if there's a car up front, so the paths will collide, so the car will brake, and then the leading vehicle goes, then paths are available, then it will start moving again, something like that. Instead of doing that, I thought, okay, why don't I choose a target point that's say 5 meters behind the leading vehicle, and then my desired position will be that target point, the target speed of the leading vehicle, and the acceleration of the leading vehicle. After that, I take that desired point and my ego vehicle's initial position, and then I connect a quintic polynomial. Another problem is with checking if the path is valid for collision. So the way I saw most people do this is by checking if these individual points are inside the building blocks of the obstacle. However, this basically models the car as a single point. Since the car is not a single point, it has a length and width. If it comes here, it will collide. So I thought, okay, let's model the car as a circle, and the future position that the car will go to are also modeled as circle. So now if this circle overlaps, I can say that, okay, this path will overlap in the future. So if you look at the difference to the left and right, the paths in the middle are rejected because of that. Another thing was with deciding how to sample the trajectories. So say if this is the global path, before my planner was sampling say 1 meter to the left of the global path and 1 meter to the right of the global path. So what happens is that, for example, this path 5 and path 1, both of them have the same cost value, and the cost is calculated by the jerk by its offset and by the time it takes to converge. Since 1 and 5 have the same thing for all three of them, the cost function will be same. So one time the car will be like, or I'll go to 1, again it will be like, or I'll go to 5, 1 5 1 5. By the time it makes some decision, it's already quite close, and because of its indecisiveness, it collides. Another problem is that if my ego car is here and my obstacle is here, since my search space is only in here, even though I could go like this way, since the search space is constrained here, all the paths are rejected. So this is also another problem. So I thought, okay, I will move my search space based on the offset of my ego vehicle. So as a result, in here, the search space is moved, so this path is not in here anymore. However, this new path comes here, which is valid. This also solved this hesitancy problem. So if the car moves even a little bit to the left, the search space also moves to the left. So this path over here is gone. So now over here the offsets are not the same, so it's not symmetric anymore. As a result, the car does not hesitate anymore. Um, Another thing I've noticed was that whenever I was calling functions which had to iterate through large lists, it was quite slow, and Python loops are very slow, and its dynamic typecasting during every runtime is also inefficient. So I decided to code those parts in C++, compile them, and then import those share objects into the Python implementation using C types. After that, I did get noticeable speed increase, so that was good to see. So this is a demo. I will increase the playback speed. So we can see that the car avoids obstacle quite well, and it's also following the global trajectory pretty well. However, when a car is moving, for example, like this, the obstacle is also moving, there is some hesitancy in overtaking it. I will talk about that a little bit later again. Right now, the car's trajectory changed to the leading vehicle following method. So right now it's following the vehicle, and now again it's back to the velocity keeping method. So yeah, this is it. Um, this is a similar situation. However, there's an interesting point that I wanted to show. Okay. So in here, just keep in mind that it does not go back again to the center. I will come back to this later again. Okay, and then this is the part about stopping. So if, for example, if there's a red light and there are cars up ahead and no way to move, the car will stop quite nicely. So what are the limitations of the current build? So you can see here that this Tesla here is colliding with the Coca-Cola truck. The reason for that is that I'm using circle-based collision system which has fixed radius. So the circle's shape does not adapt based on the size of the car, and clearly the Coca-Cola truck is larger. As a result, the front and rear of the Coca-Cola truck is outside the circle's diameter, so the car thinks that there is nothing in there, so it just goes in there and collides. So the solution for that is probably maybe to use an ellipse instead of a circle, and the major and minor axis of the ellipse will be based on that length and width. However, I found that finding the overlap between ellipses of different shape is a little bit difficult. So I tried to implement this technique called separating axis theorem. This is usually used in game development, where they check if two boxes overlap with each other. So I implemented that. However, in my first trial, it seemed that um, say a box is here and another box is around say a box is here, another box is here. Even though there is no overlap, for some reason the bounding box's coordinates are quite large, so the separate axis theorem says that it overlaps. I did not refine it, so maybe if I refine it and check properly I can find the problem. Another problem is here. Let me replay this once again. So this is the overtaking maneuver, but the car tries to go to the global trajectory quite quickly, and as a result it becomes quite dangerous, so the car stops. So what's the solution for this? The solution for this is to decrease the cost of the lateral offset of the path. However, if I decrease that, remember this part over here, this what happens. So if I decrease that, when there's a straight line, it does not go back to the center again. So I thought maybe I will include an integral kind of component, so the longer it stays away from the offset, the cost continuously keeps on increasing. So hopefully that will solve that problem. So so current work right now. So since the code runs on most general cases, currently I'm not working to solve the aforementioned problems. I'm studying how to parse information from real-world HD map and the integration of my planner to an existing autonomous system. The behavior layer of my local planner is also quite bare bone, so as it does not use any perception information. All the decisions are made without any perception. So it's to be expected that the addition of perception layer would improve the decision making of the car. And I also like a month or two ago, saw a paper, not a paper, like I saw this news about a friend optimal trajectory which uses reinforcement learning. uh, I believe the paper is still under review. I asked the author if I could read it, but I did not get any response. So I will check on that again after I'm done integrating my code to the autonomous vehicle. Thank you once again, and also thanks a lot to all the TAs in the lab, all the group members in the lab. They were very helpful. Thank you so much.